Well, hi everybody. Welcome to our third installment of part three. And this is going to go hopefully quickly because it's just a few things here and there that we need to pay attention to. So we're going to get started with our opener right here, which is, can you count how many carbons are in cholesterol? So let's go ahead and take a look at that. Please give your response for how many carbons are in cholesterol in the Ed puzzle. All right, so let's take a look at where are they all located. What's cut off the side of the screen here is that this is an OH that's attached here. That means that every other place where there is a juncture, there is a carbon located. So we have to be able to count them all up when we go through all of these. And so I'm just making a note of where you're going to find every single carbon here. And as you can see, there are a lot of them. And I think by my count, I came out with 27. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So you should have come up with 27 carbons. Okay, so let's go ahead and move things along here to what is isomerism. You know what a molecular formula is. A molecular formula shows the numbers and types of the elements in the compound. So there's CXHYOZ, given the fact that we might have some carbons, some hydrogens, and some oxygens. We also might have a structural formula where you have the carbons attached to different things like this. And as you already know, those are structural formulas. And but when we have an isomer, we have a same molecular formula, but different arrangements of atoms. So we might have a structural isomer, which means that we have moved the atoms around. We might not have the same order of bonds, but we would have the same number, in this case, of carbons, hydrogens, and oxygens. So let's just say, what if we had the oxygen in the center like this, and we ended up with hydrogens all the way around it, with these like this, and then this like this. That would be one way we could show a format of a isomer of this thing as well. And you might be wondering, well, how do I know that that's an isomer? If it has the same molecular formula, in this case, 3 carbons, 1 oxygen, and a total of 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So let's count it up. 3 carbons, 1 oxygen, and 3, 6, 8. So we have an isomer, and they are a completely different type of structure. So that's what we mean by a structural isomer. Okay, so we can go on to other different kinds of isomers called a stereoisomer, and we're going to set that aside for the time being, other than you need to know that it's a different arrangement of elements around the carbons. Okay, so that's going to be a stereoisomer. A lot more of that will be coming next time. So we're going to move this along then to, well, what can we draw the structural isomers of the alkanes up to C6? So we can draw all of the structural isomers of alkanes, but let's just focus on C6. And since this is an alkane, we're going to follow the format of CnH2n plus 2. So if this is C6, that makes this H14. So all of these isomers must follow C6H14. So let's make sure that you understand how to answer in the Ed puzzle. In the Ed puzzle, the first one that you might write down is CH3, CH2, 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 CH3. And that's going to be how I want you to respond in the Ed puzzle in the condensed format like this. And that's going to be the first of the isomers. So please go ahead and take a moment and write out the rest of the isomers in your answer box. And so then let's take a look at what they all should be. Okay, so one of the ways you could do this is you could reduce the carbon chain by one carbon and make that be a a part that hangs down from the carbon chain. And so we end up with CH3CH with a CH3 attached, followed by CH2, CH2, 1, 2, 3, 4, 5, and CH3. That's going to be 1. This CH3 is the same whether it's bonded to this carbon or this carbon. Another one that you could have is a CH3, CH with a CH3 attached here, followed by another CH with a CH3 attached here. And I've used 1, 2, 3, 4, 5 carbons, followed by a CH3 right here. So there's another version of it. You could also have a CH3 bonded to a carbon with another CH3 here and another CH3 here, bonded, that's a 3, bonded to a CH2 and then a CH3, and that would be another one. 1, 2, 3, 4. And I think that that is all of them. If I've left any off, I'm sure that you will let me know in the text box in the Edpuzzle. Okay, so let's go ahead and move this along then to our couple of conventions that we use. When we are using a curved arrow, this is different than just a straight arrow from reactants to products. When we are using a curved arrow, we are using that curved arrow to show the movement of electrons. So let's say that we had a carbon to hydrogen bond, and we want to show the movement of the electrons out of the bond to maybe bonding with something else. Maybe in the case of the oxygen to hydrogen, the bond going to those 2 electrons right there, or being able to say that, okay, what we're making is breaking off this hydrogen, so we end up with a carbon that is now deficient of electrons, needing electrons, but we end up with forming the hydrogen to OH bond like that and making some water. Okay, we also might have something called a fishhook, where you get a single-sided arrow movement of 1 electron, but if you have a double hooked arrow, that would be referring to 2 electrons. So this is just a couple different ways to do arrows, and don't worry, you will hear a lot more about this from me as we go along. So as normal, single arrows show reactants to products, and double-headed or front and back arrows show equilibrium. That's not a big surprise for anybody. So the other part is being able to show, understand molecular orbitals, s orbitals, p orbitals, that kind of thing. So when you have just the same kind of orbital bonding with each other, as in a hydrogen bonding to itself, so let me go ahead and draw in the hydrogen bonding to itself, that is really an s orbital bonding to an s orbital, just like that. And so there is a 1s to 1s overlap. The sigma bond in between these is an axial bond. So it's in between these. It goes along the axis of the atom. So they're along the bond axis. But these kinds of sigma bonds are not only found in s orbitals. They can be found in p orbitals as well. And I think that you've heard that from me before. So we're going to move things along here. So what about a hybrid orbital? So for instance, in the case of carbon, you might think, well, it has 1s2, 2s2, 2p6, or 2p2, excuse me. So that looks like it has 2 s orbitals and 2 p orbitals, and it does. But when it bonds, it exists by bonding the same way in all cases. So we end up with 4 equal distant and equal sized bonds, because what you end up with is you have the hydrogen bonding with its each 1s electron. So you have 4 hydrogens bonding with s electrons, and carbon has some s and some p. And you've already gotten the idea that when an s orbital bonds, it looks a lot like this, but when a p orbital bonds, it might look a lot like this, with this being your s and this being your p. And as you can see, those are 2 very different sizes of orbitals there, but yet when we draw the methane molecule, we end up with the same length and strength of bonds, and that's because what we're making is a new kind of orbital called a hybrid orbital. We can have these be with sigma bonds, or later on you're going to see with pi bonds. Those can be part of the orbital as well. Let's go ahead and move ourselves along here. And we did some example already. In this part here, basically the ones that we need to know are the names of them. So we can have some atomic orbitals. Let me see if I can list them down. In the case of 1s and 1p orbital making a bond, we end up with the sp as the name of a hybridization. Number of hybrid orbitals will be 1. The shape on this will be linear and 180. What if I have 1s and 2p? So I end up with sp2, and that's going to be 2 hybrid orbitals. sp2 oftentimes that implies that we have, that means that we can have a trigonal, and I'm second guessing myself, a trigonal planar situation. And then we can have 1s and 3p. So we have sp3, and that is a total number of, and I'm thinking that that should be a 3 and that should be a 4, with those being hybrid orbitals of 2 there. But that gives us a tetrahedral shape of the molecule based on the hybridization. Okay, you do not have to know any more than that for IB. So in AP they have to know more hybridization, but in IB no. All right, so we're going to move things along here. We are going to talk more about delocalized molecular orbitals, but we're not going to worry about them at this time. So we are going to get into the classification of organic compounds. We oftentimes have straight chain carbons, which we've been representing as just a straight chain of carbons all bonded to each other. They could be branched, they could be unbranched, but we can also have cyclic carbons. So carbons that are, let me go ahead and draw this correctly. Let's just say we have something like this where they are bonded in a circle to each other. They could also be multiple rings joined, as you saw with the cholesterol in our opener today. So there's that. Let's make sure that we understand the carbon. Let's go ahead and move on to our functional groups and be able to list things by functional group. So we can have a functional group listed as an alkane, and let's just make sure that we understand what is a functional group itself. Usually this is a group that is attached to the main carbon chain. It might be included within the carbon chain, or it might be included attached on the outside of the main carbon chain. Okay, so if we have an alkane attached to the main carbon chain, that is usually going to be some kind of single bonded carbons that is attached to the main carbon chain. So single bonded carbons attached to the main carbon chain. We could also have something called an alkene functional group, which ends up being, and I'm sorry for that, that my computer does funky things, a double bonded carbon chain. And that means that I need to erase. That means this is going to be like that. Okay, a double bonded carbon chain attached to the main carbon chain. So my R is going to represent here the main carbon chain. R will be main carbon chain. Okay. What about if we have an alkyne? An alkyne is referring to a triple bond. So we would have our main carbon chain, and then we would have the CH attached. So what we're going to have is a triple bond like that. And so alkanes, and these are all referring to things that are attached to the main carbon chain. Okay, so let's take a look at some other types of functional groups and their names and what they look like. What if we have something called an arene attached to the main carbon chain? An arene is referring to a 6-carbon cyclic bond, and you've seen some of these already. And I'm trying to draw one really pretty here for you so you can see it. 1, 2, 3, 4, 5, and there's a bond right here. Okay, so that is an arene. Oftentimes you'll just see the arene drawn like this, and then it's attached like this. So this is a 6-carbon circle or ring, 6-carbon ring attached to the main carbon chain. Okay, so those are our main carbon functional groups, but now we're going to get into some other types of functional groups that might be seen as well. Single bonds, okay, a single bond with oxygens is referring to, this one is going to be with an alcohol, so our main carbon chain, of course, will also have this OH attached to it. This is the functional group. It is called an alcohol. In organic, you will also see it called a hydroxyl group. You'll also see it called a hydroxyl group, and that is your functional group for alcohol there. Okay, so what about ether? Ether is a functional group of an oxygen that is found in the carbon chain. Okay, so ether is where you have a carbon chain that ends up having and that's going to be a 3-carbon chain, has an oxygen right in the center of it, or in some part of the carbon chain. It does not have to be in the dead center. It just has to be between 2 carbons or 2 different carbon chains. So if we refer to R as the first carbon chain bonded to the O, and then the second R with prime being there bonded to the second carbon chain, that's going to be your ether. And that's going to be the distinctive way you can tell what you have is an ether. The next kind of so those were single bonded oxygens. The next type you have are some double bonded oxygens. And so these are all going to be ways in which oxygen is included but being part of a double bond. Okay, so the first kind that you have is an aldehyde here, and I need to scroll up just a tiny bit more. Okay, I'm going to have space for all of it. The first kind is going to be an aldehyde, and this is where the oxygen is on the ending carbon. So here is our carbon chain, and then we end up with an oxygen double bonded on the ending carbon. So you end up with an O here and an H here. And I'm only drawing in the H so you can see where it is. So an example of this might be CH3, C, double bond O, single bond to H like that. And that is called an aldehyde. And yes, you must know the structures and the names of each of these types of functional groups. And so where is the functional group itself? It's this part right here. This is the identifying functional group. So what would we call this? Well, this has 2 carbons. We'll worry about naming these in our next unit, but we would call this F-aldehyde. So 2 carbon chain. Again, don't worry about the name, just need to know it's an aldehyde right now. If we have a ketone, then the double bonded oxygen is going to be on the central or one of the centralized carbons. So you would have a carbon chain here bonded to a carbon here with a double bond on it like this, and it would be bonded to the rest of the carbon chain like this. So what would this look like? This might look like this, bonded to the carbon, double bond, and then bonded to another carbon like that. Okay, and those are called ketones when they are on the middle carbon. Then we have a combination of both single and double bonds, and we're going to have the carboxylic acid is next, and it is found on the end carbon, and it follows the format of R bonded to C with a double bonded O and a single bonded OH. That's the general format of a carboxylic acid. This is oftentimes, this part right here is called the carboxyl group. Okay, a pretty common one is CH3C double bond O OH. That's called vinegar, also known as ethanoic acid, and so you've seen that one before. Our final one is an ester, and this is going to be where you see things look just a slightly bit different. You're going to have the carbon chain followed by a carbon with the double bond here and an O in the chain, and followed by the rest of the carbon like this. So that's going to be the general format for your ester. So here's what that looks like. CH3, C, double bond O, followed by an O right here, and then it is bonded to the rest of the carbon chain, so it might be CH3, just like that. And that is called an ester. So those are our names of those particular ones. We have a few more to add here, so we're going to move this along. Functional groups with nitrogen. So a single bonded amine, and then we can have an amide. And so you're just looking at some of the names right now. A single bond amine, a triple bond makes it a nitrile group. And then we have something called something with nitrogen and oxygen, so an amide group. That's the trickiest one of all. So let's take a look here. We can have the carbon chain followed by the amine group on the end of it. So it's usually at the very end. So that would be like CH3 and H2 would be the format of that, and that is called an amine. That's the name of this functional group when it is on the end like this. What about if we have a triple bond to a nitrile? So you'd have the carbon chain triple bonded to an N at the end. So this oftentimes looks like CH triple bond to the N, just like that. And the N, as you know, would have its lone pair right there. So that is called a nitrile group when there is a triple bond and a single N all by itself, no H's on the N. Then we have a primary amide, and this is the one that often gets people. So you have an R group bonded to a carbon that has a double bonded oxygen, but then is followed by an NH2 group. I think it's NH2. Yep, or no, just an NH. I'm so sorry. Just like that. And then that's followed by another carbon chain. And it's this part right here in the middle that makes that an amide. So it would look like this. CH3 bonded to a C, which has a double bonded oxygen, single bonded to NH. And then that ends up being bonded to the rest of the carbon chain, just like that. And once again, this is the functional group, making this called an amide. Okay. So that is the functional group called amide. Okay, let's go on here. All right, the last part that we want to talk about is what is it called when we have a halogen, basically any of the halogens. So oh goodness gracious. Okay, so any of the functional groups with halogens is just going to have this kind of thing bonded to it as some part of it. So those are your halogens. They get called fluoro, chloro, bromo, iodo, that kind of thing. It is just a halogen bonded to the main carbon chain. So there would be your main carbon chain. Some less well-used ones are called thiol and thiol ether. And I believe these are my last two, so let me scroll down and make sure that these are going to be my last two, and they are. Thiol looks a lot like the amide group, except it has the sulfur in it, so you end up with a carbon group bonded to a sulfur that oftentimes looks like that. Thiol ether oftentimes looks like this with the sulfur group in the center, followed by another carbon chain, and the sulfur group oftentimes has a hydrogen just like that. Or it ends up with just a sulfur by itself. And these are far less common for you to be asked about. It's far more common that the rest of those are. So I would say that this one is not needing to be memorized, whereas the rest of them you do have to memorize them. Okay, thank you everybody.